Okay, so off we go. So we are very happy to have today Marc Deisenroth from the University College of London, and he is the DeepMind Chair in Artificial Intelligence there, the Deputy Director of the UCL's Artificial Intelligence Center. He also holds a visiting faculty position at University of Johannesburg and Imperial College London. And as I understand, you spent 4 months at the African Institute for Mathematical Sciences, teaching their foundations of machine learning as the part of African Masters in Machine Intelligence, so which is also very commendable. And Marc will speak about data efficient machine learning for autonomous robots. So please and thank you.
Thank you very much for the introduction, and also thank you so much for the invitation. I mean, we had a quick chat earlier. It's a bit easier at the moment with the pandemic to virtually visit places across the planet, and so I'm very happy that I finally at least made it virtually to St. Petersburg. So thank you for having me. Yeah, I would like to give some sort of or talk about some ideas about data efficient reinforcement learning for autonomous robots, but using probabilistic models. I want to make a point that probabilistic modeling is an important ingredient when we talk about autonomous robots. So when we look at autonomous robots, then we often face 3 key challenges. So one is the challenge of modeling. So if we look at this robot here on the right side, we have a robot arm. So this is a tendon-driven robot arm, and there's a table tennis racket attached to the end effector. And now modeling could mean that we want to model the dynamics of this robot. And then the second challenge that we face is the challenge of predicting. So given a sequence of control signals or actions, we may want to predict the trajectory of the end effector and see whether it is able to hit the table tennis ball here. And then we also face a challenge of decision-making. And the decision-making problem could boil down to changing the control sequence if we see that we are not going to hit a table tennis ball. So these kind of 3 key challenges are quite important when we talk about autonomous robots. So modeling, predicting, and decision-making. And then, when we talk about autonomous robots, we would ideally take humans out of the loop as much as possible. And that requires us to, or at least the robot, to learn from data in some sense. And that means there needs to be a mechanism to automatically extract information from data. But in practice, we also face another challenge, which is data efficient learning or fast learning. That means learning from relatively small samples, a small set of samples. And the reason for this is really like a practical problem. It is very, very difficult to collect millions or trillions of data points using a robot, because if we run experiments in real life, then we have to invest time. We cannot be faster than real time, which we could do when we just had a simulator. But also we have some issues with hardware. So the more we run the hardware, the more it wears. And this is wear and tear of the robot, and eventually the robot will break if we continue running experiments. So ideally, we have a mechanism that learns from relatively small data sets. And then on top of this, we also have to think about uncertainty. So there is sensor noise or measurement noise. There are unknown processes that guide or define the dynamics. There is limited knowledge because we don't have data points everywhere in the state space. So all of these kinds of uncertainty sources we have to take into account when we build these kind of systems for autonomous robots. And today I want to focus on one particular framework, which is reinforcement learning, which is a mathematical framework for trial and error learning, but now subject to data efficiency, so that we can actually apply this to robotics in the robots in the real world. And I would like to talk about 3 pillars in data efficient reinforcement learning. One is model-based reinforcement learning. So it's a way to do data-efficient decision-making. And the second part, I would like to talk about model predictive reinforcement learning, or model predictive control in the context of reinforcement learning, which allows us to speed up learning even further by doing online planning. And in the end, I would like to talk about meta learning or transfer learning using some latent variables, which allow us to generalize knowledge from situations or problems that we have already solved to problems that we still want to solve, which are somewhat related to the problems that we already know about. So let me start with model-based reinforcement learning. So we are looking at the following problem. So we're looking at a state evolution. So the state of the system, the robot, that could be, for example, position and velocity at time step t+1, is a function of the state at time step t and a control signal. And there may be some additive noise. On top of that, in the following, I'm going to ignore this noise term because it's not interesting today for the concept I want to explain. The control signal is itself a function of the state and some parameters. So the function here is called the policy, and then we have policy parameters that parameterize the policy. So here we are talking about a state feedback controller if we look at control theory. And then the objective that we want to solve is we want to find policy parameters theta star that minimize an expected long-term cost. So the expected long-term cost I'm going to denote by J of theta, and it's an expected cost, a finite horizon cost of expected costs at each time step. So here we are going to compute expected costs given a particular controller parameterization, and the cost could be, for example, a squared distance between the state of the robot where it is right now and where it should be, so a target state. So that could be a particular cost function that we use. And we also assume that the initial state is uncertain and is distributed according to a Gaussian distribution with mean mu0 and covariance matrix sigma 0. This kind of objective, so minimizing an expected long-term cost, is a typical objective in optimal control, but also in reinforcement learning. And to me, these optimal control and reinforcement learning are very similar frameworks or similar research areas. And at a very high level, I would say that the only difference between optimal control and reinforcement learning is that in optimal control, we have to really be very specific about the assumptions that we have, and specifically we assume that we know what the transition function is. So usually we write down f is, well, in the linear case, is a linear function, or otherwise we would specify it's this particular nonlinear function. But in reinforcement learning, we don't have that specification. We do not make the assumption that the transition function is known. And when we go back to the idea of autonomous learning, where we take humans out of the loop and we learn from data, we are much more in this reinforcement learning setting than in the optimal control setting, because we don't need as much knowledge or prior knowledge in the reinforcement learning setting compared to the optimal control setting. And so I would like to introduce conceptually a very simple algorithm for fast reinforcement learning. So keep in mind that we want to minimize this expected long-term cost. I'm just going to keep that here on the slide. So it's the expected sum, it's a sum of expected cost at every time step. And this kind of like learning framework has 4 steps. And the first step is we're going to build a model, or specifically a probabilistic model for the transition function. So that's the thing that we don't know from the previous slide. We're building a model of the transitions that take us from a state and the control signal at one time step to the next state. Once we have this model, iteratively we compute long-term predictions of the state evolution given the controller parameterization. Then we improve the policy. That means we change these controller parameters so that they minimize the expected long-term cost up here. And then we apply the controller to the real system. And once we apply the controller to the real system, we get more data. And that means we can go back to step 1, we update our model, we recompute these long-term predictions, and then re-optimize this policy, and then go back and apply the controller to the system again. So this is kind of like we repeat these 4 steps until something interesting happens, and then we stop. And I would like to explain these 4 steps in some more detail now. So let's get started with system identification or model learning. If we look at this model learning problem, then we are effectively talking about solving a regression problem. So we want to find, so in regression, right, we want to find a function that maps x to f of x values. And for the sake of illustration, I'm assuming now these observed function values are noise-free. That means that the function we are looking for connects all of these observations in some way. And here's an example of such a function. So that function is something we could use as a plausible model within a reinforcement learning framework. And so I would like to come back to the challenges that we talked about earlier. So we have a model, so the modeling challenge is solved, but now we need to make predictions and then also decisions. And now if I ask the model, what is going to happen at x equals 7, and the model tells me, well, your predicted function value is around minus 1.5, then I can take that and say, okay, great, I have minus 1.5, and based on this prediction, I'm going to make a decision. For example, I'm going to accelerate now. And that may be a really bad idea because given the data that we have, there isn't really that much evidence that minus 1.5 is a great prediction, because we could have chosen other functions that solve our regression problem as well. And these other functions would give us significantly different predictions. And with these different predictions, we would also get different decisions. So that leads to, or that kind of like highlights the problem of modeling errors that we have in reinforcement learning, because this, what I just illustrated here is only a one-step prediction. So now, if you keep concatenating these predictions, you have accumulating model errors, and there's almost no hope that you can learn anything. Yeah, if you predict over, say, 50 time steps, then you have accumulating more modeling errors and you have absolutely meaningless predictions afterwards. So one way to address this is to use a probabilistic model. So you can describe what you actually know about the model, and you can use a probabilistic model that gives you a distribution over plausible functions. And if we now query this probabilistic model at x equals 7, then instead of telling us, well, the function value is minus 1.5, it would tell us, well, on average, I believe your prediction is 0, but actually I don't really know what's going on, and that's why we have these huge error bars here. So the shaded area represents how uncertain the model is. So the bigger the uncertainty, the bigger the error bars. And so it's really important to express uncertainty about the underlying function to be robust to these kind of modeling errors. And we use a Gaussian process to implement this distribution over plausible functions. So we use a Gaussian process to learn this dynamics model in the reinforcement learning framework. So that was the first step. So assume we have now this probabilistic model, this Gaussian process. Now let's think about how we can use this model to make long-term predictions. So what we are looking at is the situation here. We start off at time step 0 with an initial state distribution, and then we iteratively propagate this uncertainty through the Gaussian process to get state distributions at time step 1, 2, 3, 4, 5, up to the final time step, capital T. And I would now like to take maybe one of these time steps out and highlight what kind of problems we have to solve mathematically. Assume we have, we're looking now at time steps T, so we have a joint distribution, assume a joint Gaussian distribution on the state and the control signal. And we have a Gaussian process that tells us for a given state and a given control signal, you get the following distribution over the next state. In order to compute the distribution of xt plus 1, so that is the distribution of the next state, we have to solve an integral or triple integral where we integrate out all quantities that are uncertain. So we have a joint distribution on x and u, so the state and the control signal, but we also have a distribution on the transition function. That means we also have to integrate out with respect to the Gaussian process distribution. And if we do that, we get this red distribution over here. So that would be the distribution of the state at time step t plus 1. So problem is we cannot solve this integral in closed form. So that is, I got this only through sampling and kernel density estimation to get a representation of what the distribution at time step t plus 1 actually is. But the good news is that we can compute the mean and the variance of xt plus 1 in closed form. And then we can approximate the red distribution with this blue distribution, which is a Gaussian distribution that has the correct mean and it has the correct covariance. And now we can take the blue distribution here at time step t plus 1 and then iteratively feed it through the Gaussian process again and again. So, and then redo the same kind of approximation where we approximate the next state distribution using a Gaussian. And then we would get Gaussian approximations of all these, of the state evolution from time step 0 to time step capital T. So this kind of approach is called moment matching, where we compute the moments of the distribution we are interested in closed form. And then we would approximate that unknown distribution with a Gaussian that has the first correct first and second moment. Now, assume we now know that how to do these kind of like approximate predictions. Now let's think about how to improve the policy. And this is split into two steps. So first we compute the expected long-term cost, which is the blue term up here. And then we find parameters that minimize this cost. So keeping in mind that we already know how to predict, or at least approximately compute or determine what the distributions of the state at every time step is, and you know they will be Gaussian or approximately Gaussian, then we only need, in order to compute an estimate of j of theta, we only need to compute the expected values or the expected costs at every time step. So the writing down what the expected cost is, well, that's by definition is the integral of c times now the distribution on x, which is a Gaussian distribution. And so the good thing is that a lot of integrals can be solved analytically, depending on what we choose the cost function to be. And if we choose, for example, polynomials or some trigonometric functions or Gaussian-shaped functions, then we can compute this expected value in closed form. So what we have done up to this point is we did these long-term predictions. And I said earlier, we can compute the mean and the variance analytically at every time step. We compute the expected value here also analytically. That means we have an analytic expression for what j of theta is, or at least an approximation of j of theta, given that there's these Gaussian approximations. And so there's no sampling whatsoever involved. But that also allows us to compute gradients in closed form. All of these functions are differentiable. And so we can do this. We can write down an expression that just gives us the gradient, so the gradient of j of theta with respect to the policy parameters. And then we can use a standard gradient-based optimizer to actually solve our learning problem in the end, right? So, so we use BFGS to find good policy parameters. So there's no global optimality here because all of this is non-convex and nasty, but at least we can get local optimality. Okay, so now we have a new controller, and now the question is, what happens now? So I said now the fourth step is apply the controller to the real system. And for that, I thought I'll show you a little bit how this works in practice. So we're looking at a small or simple robot where we have this is called a cart pole system. There is a cart that is running on a track, and there is a pendulum attached to the cart. Initially, the pendulum is hanging downwards. And what we can do is we can push the cart to the left and to the right, and then find a control strategy that swings the pendulum up and balances it in the middle of the track where in the inverted position. So basically, we want to get the tip of the pendulum to the point where the red cross is. We do not make any specific knowledge about the nonlinear dynamics, except that we make some smoothness assumptions. But and I mean, we could write down, or we can write down the ODE, but we don't use that kind of knowledge. We just collect data from the system and then learn from scratch. As a cost function, we use this particular one here, which is 1 minus an exponential of a negative squared distance. And the squared distance is the Euclidean, or the distance is the Euclidean distance between the tip of the pendulum and the red cross. So there are no penalties on velocities or on control signals. It's really just the Euclidean distance that is being penalized here. Okay, so let me see whether that works. I have a video of this. Can you see the video?
No.
Okay, good.
No.
No? Okay, then.
No.
Okay, good. Let me try and share a different. Share screen. Does it look better now? You see a small video?
Yep.
Good. Okay, so here we have the cart, which is running on the track, and we apply random control signals to the cart pole system to collect some initial data. We have a 10 Hertz sampling frequency that we get, means we get 10 data points per second. The state of the system is, sorry, I should have said it earlier. We have the position and velocity of the cart and the angle and angular velocity of the pendulum. So we have a 4-dimensional system and a one-dimensional control signal. We have now 5 seconds of data, so 2 trials. Each trial is 2.5 seconds long, so 50 data points. Now, we train this Gaussian process model for the transition dynamics on these 50 data points. We do these long-term predictions and then optimize the controller based on those predictions. And then we go back to the system and apply the controller that we just learned. Now, when we apply the controller, this happens. The cart stays in the middle of the track. It doesn't solve the problem. But so the reason why that is the case is that if you look at the predictive uncertainty, then it explodes after 2 or 3 time steps, because the model has or had no data in that part of the state space where it just operated, and it thought that was the best thing it can do based on those predictions. However, now it has data in that regime or in that part of the state space, and that means it now knows with high confidence that what it did before was not particularly good, besides keeping the cart in the middle of the track. I mean, that was already better than random. But now it tries something new, and what happens next is this. So it kind of like gets the idea of the swing up, but it's overshooting like crazy. But it never had data in that part of the state space, and it's updating the model now accordingly. And it automatically learns now to slow down the swing up movement, and you can see in the next trials actually from one trial to the next trial, you can see a significant improvement. And this is all learned automatically. So now we have trial number 6 with 12.5 seconds of data. And after 15 seconds, trial number 7, it actually gets the pendulum up and balances in the upright position. We can run this a little bit longer in a test trial, so you can see that it really keeps it upright. And keep in mind, we don't penalize velocities. It's robust to small disturbances because it's a feedback controller. So it solved the problem quite nicely. Okay, so I'm going to share now the slides again. We're back on the slides?
Yes.
Yeah.
Yes.
Good. Cool. Okay, so that was this this part, and in the beginning I said one of the objectives that we have here is data efficiency. So how learning from small data sets, and so because this is a relatively standard benchmark problem, there's a lot of work in the literature also on running reinforcement learning methods on this system. So we have so keep in mind, so this work is a little bit older. So the I think the newest comparison I have in here is from 2009. But what you can see here is, so these are the references to the literature, and this is the required experimentation time in seconds on a logarithmic scale. And you can see that over, depending on the approach, you can get down to about 2 minutes of data. Coming down from more than a day of interaction time, you come down to about 2 minutes. And so compared to that, we are down here an order of magnitude faster than the best competitor at the time. And we achieved an unprecedented learning speed compared to the state of the art at the time. But also keeping in mind that we actually didn't have that many strong assumptions, or no particularly strong assumptions in the learning framework, besides assuming smooth dynamics and these kind of like Gaussian approximation of the state. We can also apply this, or we applied this to a wider range of problems, or robotic problems, such as using a cheap robot arm to learn to stack a tower of blocks using visual feedback, or even this tendon-driven robot arm that I showed earlier for learning to hit table tennis balls. Here's another robot arm that learns curling. This is work by other people, in this particular case from Bosch, where they had a hierarchical navigation task where they used these kind of methods. This is work by Andrew McCutcheon from Cambridge, where he learned to balance a unicycle using this approach. And again, Bosch used this approach also to control throttle valves in combustion engines. So it actually made it a little bit beyond the laboratory environment. So that's very, I find it very exciting that it's actually taken up, or is fairly applicable to a wider range of problems. And so I would like to summarize this part briefly. So we're looking at, or I wanted to motivate that data efficient learning is critical in robotics. And I introduced a probabilistic model-based approach that allows us to reduce model bias, that achieves an unprecedented learning speed, and is also widely applicable to different robotic systems and different robotic problems. Now, in the second part, I would like to talk about how we can use ideas from model predictive control combined with the approach that we just introduced to speed learning up even further. And one of the motivations to look at this entire problem here was to think about safe exploration. So there are sometimes real-world constraints or safety constraints that we need to consider. So the other approach didn't really do anything. So if a robot arm crashes through the table, it did not get any penalty besides not solving the problem. But we would like to avoid crashing into the table already at training time. And so what we can do is we can use probabilistic models to predict whether state constraints are violated. So you can think about this in terms of pictures, maybe like this. You do not want to hit that red line, so that's a constraint. And these are, if this is your predictive distribution of the state evolution, at this point, you probably want to make a decision, okay, let's try something else, because this is going to violate my constraint with some non-negligible probability. So what I'm going to talk about is now about safe exploration within a model predictive control framework embedded in an RL setting. And also one of the ideas that model predictive control gives us is to optimize control signals directly instead of optimizing policy parameters. So that would also simplify our optimization problem from a maybe 100 or multi-hundred dimensional problem down to, you know, how many control signals we actually need to optimize in a finite horizon times the dimensionality of the control signal. So it's typically a lower dimensional problem. So here's the high level idea. We optimize control signals directly. And as I said already, it's a lower dimensional search space which simplifies the problem. However, if we optimize control signals directly and then just keep applying them independent of what that happens, then we have an open loop control problem, or solve an open loop control problem, and there's no way to account for predictions that don't quite match reality. So that means we will never be able to adjust for predictions that were slightly wrong. And that means with very high probability, there's no chance of success if we have already minor model inaccuracies because you have these compounding or accumulating errors. So what we can do is now we can look at a model predictive control framework that turns this open loop control problem into a closed loop control problem. And closed loop means we can account for new measurements of the state. And so we're going to use this now within a reinforcement learning setting. And here's really the idea of how this works in simplified. We start off with exactly the thing that we had before, which is the Gaussian process model for the transition dynamics. And then now while we are executing the policy, that means while we are operating or working with the robot, if a robot is in a state xt, we compute or determine an optimal control signal, u0 star to uh-1 star. So h is the horizon we are considering. It's typically relatively short, maybe 10 or 20 time steps. And the key thing here is we only apply the first control signal in that state, and then we transition, or the robot transitions to the next state. Now we have one more observation of a state control pair and next state, which allows us to update the Gaussian process transition model. And then we go back, we replan. So we have now an updated model, and then we determine again the optimal control sequence u0 star to uh-1 star, and only apply the first one. The robot transitions, we update the model, we replan, apply the first control signal, transition, update the model. So this kind of repeats, and we can repeat this forever. But we also have some good theory. So practically, I think this is, it's relatively straightforward here. But we also have some theoretical results, and that comes also with the kind of uncertainty propagation that we do. So this moment matching part, where we approximate predictive distributions with a Gaussian, is deterministic, and that allows us to reformulate the system dynamics, where we effectively define a new state or belief state, if you want to, that consists of just the mean and the covariance matrix of the state. And then we have a deterministic function, or a GP could also, we have a deterministic mapping that takes the moments at one time step and the control signal that maps and takes them to the moments of the next time step. So that is, all of this is deterministic. And we can show Lipschitz continuity under some mild assumptions. And that also implies we can apply Pontryagin minimum principle, which allows us to solve the optimal control problem in a much easier way. And we can also take care of control constraints. So what I said earlier, we can look at the predictive distribution, and then if the state violates some constraints, then you just change it. This approach also now allows us to take control constraints into account. So if we have bounded control signal, let's say control signals between -1 and +1, we can now formulate this in a proper mathematical way. And additionally, we can use the predictive uncertainty to check whether the state constraints are violated as well. So that's the idea. And now we can we're going to go back to the card-pull system that I introduced earlier. I use this as a running example. We are going to look at 3 different ways to control the card-pull system. So here on the horizontal axis we have the number of trials that we run the system on. So each trial is 3 seconds. And then we have here a success rate. So we ran this for, I think, 100 experiments. So the arrow bars give you an indication of how much spread there is in individual trials. The red line is the approach I was talking about earlier. So that doesn't care about any kind of constraints. Just, I mean, in this particular case, right now we have no constraints yet. We're going to get to the constraints later. I just want to look at learning speed now. So here we use the same kind of policy optimization that we discussed earlier, where we optimize the policy parameters. And then we have the yellow and the blue line or the graphs here as well. So what the yellow line does is it learns the Gaussian process dynamics and then throws away the uncertainty. It only takes the mean prediction. And that surprisingly works within a model predictive control framework. If you were to do this in the other approach that I talked about earlier, you have 0% success rate. It will fail. The blue line is now the Gaussian process. So the full Gaussian process with uncertainty propagation. But what we see from this graph, so if we're looking at the yellow and blue curves, we achieve a high percentage of success, let's say about 90% after 3 trials. And compared to the red line, which is the other approach, the non-model predictive control approach, that exceeds the threshold of 90% success rate after 5 trials. So we shave off about 40% of the trials. I mean, it's small numbers, but still it's 40%. That means we are more data efficient than we used to be with the gradient-based policy parameter optimization approach. That means with model predictive control, we increase the data efficiency. But so the reason for this is that model predictive control increases also the robustness to modeling errors. And the reason for this is that you update the model after every single time step the robot takes while it's executing the policy. And in the previous approach, we learned the policy and then only updated anything after the full experiment is done. Whereas in the model predictive control, you update online, and that increases the robustness to these kind of like modeling errors, and that will also speed up learning. That's the reason why there is this 40% gain in data efficiency. So now we can talk about, okay, this is a different system, but so this is a double pendulum system. But we have the same kind of pattern here, that with model predictive control, we learn faster. 40%, again, 40% will be is the number that we gain. The only difference or significant difference now is that the zero variance approach, where we throw away the uncertainty of the Gaussian process and just take the mean, fails. So now the state space is more complicated, and we will not be able to solve the problem. I mean, there's a little bit of a bump here where it accidentally solves a little bit, but you can use a deterministic model for the transitions if your state space is easy enough, but otherwise you have to use a probabilistic model in order to get anywhere. Yeah, so the key message here is, although model predictive control makes the model fairly robust to model inaccuracies, we can't get away without uncertainty propagation, and that is usually the computationally expensive part. So now let's add some constraints here. Yeah. So we're going to look at the card-pull system, but now going to build a wall on the left side. So that is a constraint that we do not want to bump. We do not want to bump into that wall. And what we see here again with these kind of like 3 approaches. So the yellow one is again the one where we. No, let me explain this properly. So the red one is what it used to be before. The blue one is a Gaussian process where we do MPC and look at predictive variances to check whether the constraints are violated. And the yellow one is now a Gaussian process with model predictive control, but we only check whether the mean of the predictive distribution violates the state constraint. That means what we would expect is that the yellow curve is more aggressive but fails more often, because mean predictions are sometimes not ideal, and that kind of like is also revealed in the numbers that we see here. So we ran 100 experiments, and if we only look at the mean prediction for checking whether constraints are violated, we have about 20% violation of the constraint, whereas we are in the low numbers if we actually take the variance into account. So again, here model uncertainty or propagating model uncertainty is important for safety as well. And this is safety during training. It's not only not during testing. So the summary for this part is that I wanted to motivate that probabilistic prediction models are important for safe exploration, and we can use uncertainty propagation to reduce the violation of safety constraints. But also one of the things that I think also came across here was that using a model predictive control framework increases the robustness to model errors and leads to increased data efficiency. I would like to spend maybe another 5 or 10 minutes on a last part on meta learning, if that's okay. Otherwise, I don't know.
No,
exactly.
that's quite fine. We even started a bit later, I think, than we planned. So
yes,
yeah,
okay.
please continue.
Good, thank you.
Yes, sure, yeah.
Good, thanks. So in the last part, I would like to talk about meta learning or some way of like transfer learning. The idea is really to have a mechanism that allows us to generalize knowledge from things that we know to new things or new related problems. For example, you could think about having 4 different robot arms, and they kind of like look the same, but they also look different in some way. Right? So they have the same number of links, they have this gripper in the end, but their dynamic behavior is slightly different. Now the question is, can we exploit similarities between these robot arms to, for example, transfer knowledge from maybe these 2 robot arms to these 2 robot arms, so that we don't have to learn from scratch again? Yeah, we can think about different robot configurations. For example, the lengths of the links of the robot, or the weights of the arm, and these kind of things. That is kind of like what we would like to do. We would like to reuse experience that we have collected to generalize learning to new, for example, dynamic models or new controllers that are for systems that are similar. And we hope that we can accelerate learning using this kind of approach as well. And so the approach we take is that we're separating global and task-specific properties. So we have some shared global parameters that describe the general dynamics, and then we have task-specific local configurations that we describe using a latent variable. That we use variational inference to infer the configuration of a new task. Here's kind of like the idea. Assume we have a regression problem. So we have observations y, which are a function of x, and okay, we can have a control signal in here as well. But let's ignore the control signal for the time being. Some local parameters h and some global parameters theta. What that could be in this particular example here is, think about why. So each of these functions is offset from 0, and you can think of but otherwise the shape of the function is the same. So the true functions are these black functions, and they're all identical, except that they're offset from 0. Now, what we now use the theta parameters for is to describe the shape of the function, and the h parameter to describe how much offset each individual function is from 0. Yeah, if you were to write down y equals f of x plus h, or f of x plus h, then you would exactly get these functions here if you choose the right offset h. What we now do is we collect training data from 2 of these functions. So the training data are these black dots here, and then we use a Gaussian process for this again. So we train a Gaussian process that takes in the inputs x, a latent variable h that we infer, and then predicts the corresponding y values. So once this model is trained, we can now ask the model what happens at this point. So we give it one more data point, which gives it one x value and one y value, and then we ask what does the function look like that goes through this point. So with this one data point, we can make an inference about what the corresponding offset is through this framework. And then the Gaussian process can generalize from this one observation what the shape of the function looks like. So if we were to learn just to fit a general function only having a one data point, the only thing, or the best thing we can probably do is fitting a constant function. But here the transfer allows us to get the general shape right of the function, and that's also actually true for all of these other orange functions, where we just use one particular test point or data point to make an inference about what the offset is, but we can get the general function shape pretty well. It's maybe easier to see in the one here on top. So that works quite nicely. So we use a Gaussian process to capture the global properties of the dynamics or the general shape of the function. And we use the latent variable h to describe task-specific properties. And in this particular case, it describes the offset of the function from 0, which is task-specific, but the general shape is a global property. And we can use variational inference to find a posterior distribution on this latent configuration h, for even if we only have one observation of that function. And that allows us to do fast on an inference of new configurations because it doesn't necessarily need to retrain the model. Yeah, so retraining the model is not necessary to get this orange shape here. We just need to make an inference of what h is, and we use the global parameters that come from the other data points that we already collected to produce meaningful y values. What we now can do is we can go back to the card-pole problem card-pole system that we looked at earlier, and we now can change the length and the masses of the pendulum. So we can make the pendulum a bit longer or a bit heavier. And now the latent variable encodes or implicitly encodes the length and the mass of the card-pole system, of the pendulum in this particular case. We use 6 training configurations, which are these disks here. That means we have lengths so 50 centimeters and 70 centimeters, and masses 800 grams and 600 grams and 400 grams. So these are these orange disks. Now we give it one more trajectory from a different configuration. For example, this one here would be length 60 centimeters and mass 400 grams. So that is something that we have not observed before. And we do this for some other tasks as well. In the embedding or the representation using these tasks, the representation of those tasks using this latent variable is given here. And what we can see here is that, roughly speaking, this is a coordinate system, so where mass increases if we go along this axis, and the length of the pendulum increases if we go along this axis. And I think the interesting thing here is that it clusters tasks here, so they have a lot of similarity, and similarity now means their predictions will not be vastly different. And these tasks have in common that the pendulum is long and the mass is heavy. That means it's a very slowly moving system. Whereas if we look at the top, we have a short and light pendulum. That means the pendulum moves quite quickly. And the dynamics here are fairly dissimilar from anything that we have, anything else that we have in this kind of like configuration set. So we can use these kind of task embeddings to also figure out which tasks are similar to each other, and then maybe exploit that even to find some mechanism to cover a larger part of the configuration space of possible configurations of the card pole system, or in general the problem at hand. Now we can use this idea also to reinforcement learning again. So we're going to go back to the card pole system, and what the first thing we want to look at is whether we can use this idea of transfer learning or meta learning to speed up reinforcement learning, even if we only look at different configurations at training time. So we have access to all data from all training tasks at the same time. There's no unknown configuration at the moment. And so the obvious approach is if we just train on these tasks independently, or train the model independently, then we would need approximately 16 seconds of data to learn a good controller that solves all of these six different configurations of the card pole system. Another way we could do is we can just dump all the data and pretend it comes dump into one data set and pretend it comes from the same model. So that means we aggregate all the data. And in this case, we would the training would take a bit longer, or we can use aggregate the data in one data set, but now we use latent variables that allow us to make distinctions between individual tasks. And what we get out here is that it's a little bit faster than the independent training. That means even at training time with fully known tasks, this approach can be useful. But the really interesting case is where we now use these 6 training tasks to kind of like warm start learning of 4 unseen configurations. So now we're going to use configurations that we do not have in our training data. And our idea is, or what we want to have is, we want to have a controller that allows us to solve all 10 tasks. So that means the 6 training tasks and the 4 test tasks, so we don't forget anything that we already learned. And again, we can do the independent training where we just start independent controllers, and we need about another 7 trials to make sure to nail these additional 4 test tasks. So that's okay. The aggregated task, where we just throw everything into one data set, but we cannot make a distinction between individual tasks, will not really get to a point where it succeeds. And the reason now for this is that the tasks are sufficiently different that the inferred noise or uncertainty, say the differences in the tasks are now interpreted as noise, and with so much noise, it's very hard to learn. So it doesn't really get over the 80, definitely not 90% success rate. But if we use this approach with meta learning, where we use these latent variables to make the distinctions between individual tasks, we have a warm start at around 35%. And after around 3 additional trials, we get to an 80% success rate, and around 90% we get already after 6 trials. So that is, I think that's very encouraging here, and that allows, I would say, meta learning gives us a warm start when we want to solve new problems, and it generalizes really, or reasonably well, at least to unseen tasks. So it allows us to learn, to actually transfer some knowledge, something useful from something that we have seen before to a new problem. So to summarize this, what we wanted to do is we wanted to generalize knowledge from known situations to unknown situations to facilitate few-shot learning. And we can use this latent variable, this h here, to infer task similarities. And we've seen that we can achieve a significant speed up in model learning and also in model-based reinforcement learning. And to summarize all of this talk, or the entire talk, I really wanted to make a point about data efficiency as a practical challenge for autonomous robots. We talked about the three pillars of data efficient reinforcement learning. One was model-based reinforcement learning, where we used a probabilistic model for fast learning from scratch. Then we looked at model predictive control with learned dynamics to accelerate learning and allow for safe exploration. And then the meta-learning approach in the last part that uses latent variables to generalize knowledge to new situations also accelerates learning. But key to success in all of these approaches was probabilistic modeling and Bayesian inference. So thank you so much for your attention. And if you have questions, please ask.
Okay, thank you very much. So are there any questions?
So I have, yes. So it would be kind of a set of questions in one question.
Okay.
So first of all, you showed us a discrete time dynamical system as your control. And of course, all the systems which you had shown to us was control systems driven by ODEs, by differential equations. Does it really make a sense? Is it important or not?
I think so. That's a good question. I think that we can do continuous time. I mean, the continuous time will come with some more difficulties, but maybe. I mean, I haven't. To be honest, I have not looked into continuous time control at all. I believe there is room for doing something in continuous time, but I'm a bit worried about the problems that we have to solve in order to get this working in continuous time.
My question was partially motivated by the fact that this, when you say you was speaking about propagation of Gaussian mean and this variance, I'm not expert in Gaussian stuff, yes, at all. Then it's possible to do some linear approximation. It is a proper way to do this.
That's correct.
So might be it's possible. And my question was it already inside or it's not inside here? Yes. And I understand your answer that not yet.
No, it's not yet.
Yeah, and then it's even more surprising that it is so successful because you approximate ODE by discrete time and it works.
I mean, it depends on your time discretization, right? So if you look at nonlinear functions and you just approximate this very locally, then a linear approximation is often quite good. Then, I mean, there come some practical issues with this. If you make it very small, you no longer have a signal because then there's no more difference between different time steps. So what we actually like to do is, I mean, what I said earlier, we have a sampling frequency of 10 hertz. It's actually fairly large given in control. Normally you would say, let's just go for 100 or 1000 hertz. But if we do that, then we have no differences anymore. So the signal to noise ratio is far too small to learn anything.
Yeah, and a second would be a comment, might be not a question, but at least to this pendulum, which is upward. It's actually kind of known that it's not only you can create a stable control there, but also that you can find a frequency with which you can, turbulent your base such that the upward position becomes stable. So did you pick up the stable controller or you picked up this stable regime by itself?
I mean, we chose the sampling frequency based on the natural frequency of the pendulum. So that depends on the length of the pendulum. So that's how we set at least get a ballpark of the sampling frequency. but the controller itself is a neural network. So all guarantees are out of the window here.
Yeah, no, but the result, what it picks up, the stable control, is dynamical phenomenon, or stable fixed point as a dynamical, not controlled phenomenon.
So we haven't looked at stability or convergence at in this. So the control itself, right? So if you remember back the video, right? So the cart was still moving around.
Yes, no. I have seen
right?
that car is moving, and this is exactly, so you can find actually a frequency with which it will move, such that the position near the cross will be a stable point of
so
this.
it looks like it finds this, but I cannot give you any guarantees that it will. But it looks like it, right? It's
yeah.
Because the tip doesn't move.
This is why I'm asking. Yes.
Yeah.
Okay, so might be I will leave a room for other people. So.
There any more questions?
So I have two sort of soft questions. So one is how good practically a Gaussian model is the model for sort of random effects you have, because it's sort of inherently linear, but not all things are linear.
I mean, yeah. So there are obviously limits to the Gaussian approximation. I mean, you probably also, I mean, you remember this this picture here, where the Gaussian is really a horrible approximation. It's a really bad approximation to linearize the function here. But what we observe is something interesting. If you, let's say, here's an example. You have a pendulum that is upright, and it can fall in this or in this direction. So if you were to model it this way in an uncontrolled pendulum, then you would have a bimodal distribution. And if you were to approximate this using a Gaussian, you would be in a really bad situation. Because I mean, the mean is wrong in the first place, and then you have this huge variance. But here we have a controlled system that means we can decide, we can push it actively into one direction, and then make this a unimodal distribution. And what goes hand in hand here is the quality of the approximation in this moment matching and the quality of the controller. If the moment matching approximation is bad, the controller will be bad as well. And then overall, the learning system figures out some sort of combination of a good Gaussian approximation and a good controller that solves the problem. I'm not saying anything about optimality, but that is kind of like some features of the Gaussian approximation within this framework. If we were to look at more interesting distributions, for example, we can sample. Yeah, we can sample trajectories, and then we have particle representations, or sample trajectories which are non-Gaussian, even marginally are non-Gaussian. Then we could have a much more expressive distribution of predictive or future states, and would give us much more flexibility. So we're looking at this at the moment, but it turns out that within this particular learning framework, the moment matching approximation is shockingly good. Whereas if we were to sample trajectories, for example, with the different initial conditions, we would get, for example, we could get bimodal distributions, and it actually struggles to be better than the moment matching approximation. So there are ways to getting better approximations than the Gaussian, but we need to look at problems where this actually pays off.
But you say that it's good like for all the possible problems, or only for some problems where it worked and for others nothing works?
So so one, I think, a situation where the Gaussian approximation is probably really bad is when you have contact, right? So when you hit the wall somewhere, because there's no probability mass on the other side, and that would be, I think, it would be a great case for a different for a sampling representation, because none of the samples will go through the wall, whereas in a Gaussian approximation you would have probability mass behind the wall, which you cannot, which makes no sense. But these kind of, you know, we are working on this, but you know, we're still looking for examples where we can beat the Gaussian approximation.
And what happens if you plug in like a problem which you can't solve? So for example, let's say parking a car is a very nice and stable problem, then parking a tractor trailer is sort of less stable but doable, or at least truck drivers do it. And I know that people who did robotics before all this machine learning kicked in, they did it very well. But there is a sort of a geometry theorem that if you have tractor trailer containing, say, 4 parts, you cannot possibly park it. So there are some configurations into which you cannot possibly get in.
Mm-hmm.
But for example, if you plug in this problem and try to solve it, what will happen?
I mean, there are ways of incorporating constraints into, well, maybe not directly into this particular setting, but there's some ways where we can incorporate constraints, for example, explicitly mechanical constraints or other geometric constraints that will also simplify.
For this one, I just want to specify that it's like kind of symplectic geometry constraint. There are some invariants which will always be the same. So it's kind of a theorem you prove. So a priori, it's not clear that you cannot get to any other point of state space, but there are some invariants. There are some integrals of motion, so you still keep somewhere. So it's like parking car where you cannot turn the wheels, you just roll back and forth. But here I think it's sort of more complicated because you are, if I recall correctly, you can get arbitrarily close to your point, but in some very roundabout way, but you can get exactly. So it's.
Yeah, so I mean, I think we need to look into this a bit more closely. I think the tractor example is maybe a good example to think about. But yeah, so I can't really say much more about this this particular example.
Okay. Okay. Well, thank you. And other questions?
I have a small question. Well, maybe not so small. These dynamics that we end up with, the deterministic one, where we take mean value and covariance matrix at this step to the mean value and covariance matrix in the next step. So this approximates some real dynamics of the same mean values and covariance matrices, because yeah, we didn't use the proper distribution at time t+1 to evaluate time t+2. So there at time t+2, there is some error in this. So did somebody study this, the error properties of these dynamics, and so how it behaves?
Define study. Not thoroughly, as far as I know. We only looked at some empirical results, but there's no theory behind this. If you mean like theoretically, yeah.
And empirically, the result is basically for a few time steps it behaves okay, and then it starts to behave really bad.
So the empirical results we have is that the uncertainty estimate is very conservative. So we often end up with an overestimation of variance overestimation rather than underestimation. So the variance are a bit on the larger side. That can happen. We haven't really seen that much problem with like underestimation. That can happen very early on in the learning stages when you only have a few data points and the model is completely off. But otherwise, it's more variance the variances, the predictive variances are too big. That means the real data will, with some reasonable probability, lie within whatever the 95% confidence bounds.
And also you said that you've tried to do some sampling to approximate actual distributions instead of this moment matching Gaussian approximation. And so the question is, have you tried to use sampling to better approximate means and covariances? So same Gaussian approximation, but in this setting, you use samples to estimate mean and covariance, and then there is a chance that you better estimate only these two moments on the long time periods.
Oh, so you would use the sampling in exactly this this setting here that is on the slide, where you would sample means and variances instead of like full trajectories?
No, I mean, you can sample full trajectories to better estimate means and variances on like a long-term trajectory.
Oh, so then you would use the sample trajectories and then use, for example, a Monte Carlo estimator to get a mean and a variance at each time step. We haven't done this because, I mean, I think it's a good exercise to see how bad the moment matching means and variances are, or how accumulating the error is. But the question, so I think that would be good. But if we were to control or use this for control, I would rather use the sample trajectories, because then we are not restricted to means and variances, because then you have a much richer distribution using particles. Sorry, a much richer representation of the distribution if you use particles.
Yeah, I see. But so the motivation was actually that you mentioned that when you use these, you end up with worse results than with moment matching. So I thought maybe you can do better moment matching, and with this you can do better results in the end.
Yes. So there's also the question of computational complexity. So the sampling turns out to be a little bit, factor 2 or 3 slower than doing the moment matching directly. So you need to, so if you want to do sampling and then use the samples to compute means and variances, I think it's worthwhile investigating whether we get anything out of this. But again, I would like to, I think we need to look at problems where the moment matching really catastrophically fails to justify the sampling approach. I mean, but in this case, the approximate moments would also not work. So I mean, I think in the setting that you mentioned, we would need to find a problem where the moment matching that we use at the moment, the iterative moment matching, fails, but the moment matching using the samples succeeds. And so it's a bit unclear to me how to characterize or how to find the settings where that is actually the case. So I think it's good to think about this, but I don't have an application area. But on the other hand, using the sampling to empirically estimate what the true means and variances are, and then see how the error accumulates over time. If you do this iterative moment matching, I think that is definitely worthwhile investigating, independent of whether it has an application or
not. Thank you. And the last question is, what's kind of the data efficiently state of the art right now?
Depends on what kind of problems. So if you look at the simple problems that I talked about today, I believe that these approaches are still state of the art. I mean, it's also difficult to get significantly better, to be honest, right? Especially in the MPC setting, we need like 10 seconds of data. I mean, how much can you do with less than 10 seconds? But if you look at more complicated problems, then, you know, all of these kind of like methods here, they only work in situations where the dynamics are smooth. Yeah, ideally no contact, for example, the contact is bad, and in relatively low or moderate dimensions. So in terms of dimensionality, the biggest problem that I used this on was like 30 dimensions ballpark. If you want to go to hundreds or thousands of dimensions, then all of this, I think, will also fall apart. But an approach to, or one way to address this is to put in some structural knowledge about the problem. So you could maybe learn lower dimensional embeddings. So if you know that your true state lives on a lower dimensional manifold, you can use that. You can use some structural prior knowledge. For example, if you bake in some geometric constraints or some mechanical constraints or physical constraints, then you can also simplify the learning problem, and you would get a speed up from there as well.
Mm-hmm. Yeah, okay, thank you.
Well, thank you very much for a nice talk. And well, we will hope sometime to see you in person and not only in Zoom.
Yeah, thank you very much for the invitation. It was great fun. Also, thank you so much for the questions. A lot of stuff that I need to think about more. And if you have any kind of like follow-up questions, please send me an email. And yes, I do hope that we actually meet in person at some point. Yeah, but thanks a lot for having me.
Okay, thank you. Bye.
Bye.